All right, today we're talking about a search algorithm that's got a really clever safety switch built right in, depth-limited search. We're going to see how it takes a classic algorithm, depth-first search, and adds one simple little rule to stop it from going completely off the rails.
So just imagine this for a second. You've got an algorithm exploring a giant maze, looking for an exit. But what happens if it picks one path and just never stops? It could wander down some endless corridor forever, totally clueless that the exit was actually right back near the beginning. That's the exact problem we're going to solve today.
Okay, so to really get why depth-limited search, or DLS, is so smart, we first have to talk about what it's fixing. We need to look at the big, glaring weakness in its predecessor, the standard depth-first search.
The strategy for a regular depth-first search is super simple, almost stubborn. Its one and only goal is to go deep. It picks a path and follows it all the way to the very end, and only then does it even think about going back to try a different route.
And right there, that's where DFS can run into a massive problem. What if a path doesn't have an end? In a really complex graph, some paths might be infinite or get stuck in a loop. DFS will just follow that single path forever, completely lost, never realizing the answer was just one turn away.
So, how do you fix a problem like that without totally rewriting the playbook? Well, the solution is actually beautiful in its simplicity, and the clue is right there in the name: depth-limited search.
DLS is pretty much just DFS, but with one crucial new rule. It still goes deep, but only up to a limit that we decide beforehand. This limit is like a safety net. It stops the search from just wandering off into infinity. Think of it as DFS, but on a leash.
So for our example, let's just pick a number. How about 3? This means our algorithm is not allowed to explore any node that's more than 3 steps away from our starting point. This one number is the key to the whole process.
All right, that's enough theory. Let's actually put this thing to the test and see how DLSS works in a real example.
Okay, here we go. We're starting at node A. And since this is basically DFS, we're going deep. First stop, B, that's depth 1. Then we go to D, that's depth 2. And finally, we push on to node F, which is at depth 3.
And stop, right there. We've hit our depth limit of 3. DLS literally doesn't care if there are more paths leading out from F. The rule is the rule. We cannot go any deeper, so our only option is to turn around and backtrack.
So we go back from F to D. From D, we look around. Are there any other paths we haven't tried? Yep, there's G, so let's explore it. We go to G, and what do you know? G is also at depth 3. We've hit our limit again. No further down this path.
Okay, so after hitting the limit at G, the algorithm backtracks. And since there's nothing left to explore from D, it backtracks again, all the way to our starting point, A. It's exhausted that whole branch. Now it tries the next path, starting with node C. From C it goes to H, and from H it tries K.
And there it is, goal found. K is our target. And the really important part, we found it within our depth limit of 3. The search was a success, and we never once risked getting stuck in an infinite loop.
So it worked great in our little example. But, every algorithm has its trade-offs. Nothing's perfect. Let's break down the good and the bad when it comes to using depth-limited search.
Okay, let's look at the stats. First, is it complete? Meaning, is it guaranteed to find a solution if one exists? Well, no. If our goal was at depth 4, our limit of 3 means we would have missed it completely. Is it optimal? Does it find the best path? Nope. It just finds the first one that fits within the limit, not necessarily the shortest. Performance-wise, it can get slow because the time it takes grows exponentially with the limit L. But here's the big win: space complexity. This thing is super memory efficient because it only ever has to remember the one single path it's on at any given moment.
When you put them side by side like this, the trade-off becomes crystal clear. Regular DFS might get stuck in a loop forever. DLS fixes that, but it creates a new problem. It might fail if your limit is too small. But look at the performance. By swapping out a potentially infinite fifth D with a fixed limit L, DLS gives us a predictable, contained search. You're trading guaranteed success for guaranteed performance. Okay, so with those limitations in mind, when would you actually choose to use DLS? What's the perfect situation for this algorithm?
This is it. This is the #1 reason, right here. You pull out depth-limited search when you are staring down a search space that is just massive or maybe even infinite.
It's the guardrail that stops the simple DFS from driving right off a cliff.
So we fixed the infinite loop problem, which is awesome. But in doing so, we've created a new headache. What if you set the limit too low and miss the goal entirely? This leaves us with a really interesting final question. If the limit is so important, how do you pick the right one? And what if you didn't have to pick one at all? Well, that's a puzzle for another time.